Hello everyone, this is lecture 3 of week 12. Recall that in the past 2 lectures we learnt the basics of supervised learning, right, where we have labeled data set given to us, and we assume that the label y is related to the feature vector x by y equal to f of x, and we minimize a given loss function for a given text vector, right. So, I mean the task is to estimate f of x naught for a given test vector in such a way that it minimizes the given loss function. Okay. So, and then we went to a special case when f is assumed to be linear, that is a simplifying assumption, right, and the loss function is given to be squared loss function. Okay. So, in that case, so we had the OLS, the ordinary linear ordinary least squares example, right. The OLS method, we discussed about it and gave the closed form solution. Okay. And then so a similar method was also proposed, which is called as the ridge regression, right. So, in ridge regression the objective is only slightly different, right. So, in OLS we just minimize the sum of squared loss of in each of the data points, right. In ridge regression, instead of just minimizing this, we are minimizing this with respect to some constraint on the parameters beta naught, beta 1, dot beta p, right. So, that is the sum of squares of beta 1, beta 2, dot beta p should be less than or equal to some quantity s. Okay. So, that is the constrained optimization way of writing the ridge regression problem, and there is also an unconstrained optimization way of writing the ridge regression problem. Okay. So, we discussed about both of these and you can see that on the screen. We have 2 boxes, the box on the top, right. So, that refers to the constrained optimization version of the ridge regression problem, and the box on the bottom refers to the unconstrained optimization version of the ridge regression problem. So, this was one reason why I chose this example, I chose this method ridge regression to be implemented, because I could implement both constrained optimization algorithms and the unconstrained optimization algorithms that we discussed throughout this course. Okay. All right. So, one of the questions that is still pending to be answered is, how do we choose these parameters s and mu? Okay. So, suppose we are given the data, the labeled data x1, y1, x2, y2 that we discussed few classes back, right. Yeah. So, this data tau which we have, suppose this data is given. Okay. We cannot just go ahead and solve the problem like what we did in OLS, because we need the parameter s if you are solving the constrained version, or mu if you are solving the unconstrained version, right. So, that is a question which needs to be answered. Okay. So, in practice what we do is I mean we try different values of s. Okay. And I mean we choose the value for which the testing error is the minimum for I mean the value of s for which the testing error is the minimum. Okay. So, that is exactly what we do. Okay. So, yeah, we will see that when we write the code for ridge regression. Okay. Nevertheless, so another important question that we have is, so I said given the data we need to choose the values of s and mu, right. But the first question is, where is the data? What data are we going to use to solve this ridge regression problem? Okay. So, the data that we are going to the data set that we are going to use is called as the Boston housing data, okay, of 1970. Okay. Okay. So, it is housing data set. Okay. So, yeah, this is publicly available. So, let me show the data to you in the first place before moving ahead. Okay. Yeah, this is the code that we had in the last last week. Okay. Fine. So, this is actually available in Carnegie Mellon's Carnegie Mellon University's website. Okay. So, yes, this is what it is, lib.stat.cmu.edu/datasets/Boston. Okay. So, yeah, this is the, yes, I think now it is clear to you. So, this is called the Boston house price data as mentioned here. Okay. So, let me explain this data, what this actually means. Okay. So, this is actually a labeled data set. I mean, though when you just look at it, it does not look like that, right. So, the first 13 variables, okay, so that you have here, CRIM, ZN, INDUS, CHAS, NOx, RM, age, DIS, RAD, tax, PT ratio, B and LSTAT. So, these 13 parameters, right. So, these are the independent variables, the feature vector. Okay. The last one, MEDV, that you have here, right, the median value of the owner occupied homes in thousands of dollars. Okay. So, this is actually the dependent variable. Okay. So, given these variables CRIM, ZN, LSTAT, okay, I mean we need to find the median value of owner occupied homes. Okay. So, the training data is given to us. I mean there are so many data that you see here, right. So, yeah, if you do not understand this, it is like this. Okay. So, you have 14 data points, right. So, 14 points in each of the data point, right. So, this refers to CRIM, okay, and this value refers to ZN, this value refers to INDUS and so on. So, these 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. Okay. So, the 13 of them that you see here are the independent variables. So, when the independent variables are these 0.00632, 18, 2.3 dot, then the dependent variable turns out to be 24. Okay. To explain this even further more clearly, right. So, just check what each of these variables mean. Okay. This CRIM actually means per capita crime rate by town. Okay. So, this is the house price data of Boston city. Okay. So, in Boston city there are different towns, different areas, right. So, I mean in each of the cities here, I mean you might know that there are different areas, right. So, I mean if you are from Delhi, right. So, you might know that yeah, there is a place called Chandni Chowk, there is a place called Connaught Place and so on, right. There is a place called House Khas, right. So, these are different towns that you see in Delhi, right. So, in a similar way Boston has different places, right. So, in each of those places the data points vary. So, there is I mean this per capita crime rate is different for in different places, right. So, there are places where the crime rate is high, there are places where the crime rate is low. So, in each of the places the crime rates are given. Okay. So, in one of the place it is 0.00632, in one of the place it is 0.02731 and so on. Okay. And the second one refers to proportion of residential land for over 25,000 square feet, and the third one refers to proportion of non-retail business acres per town. Okay. So, in each of these places you will have certain percentage which are residential area, you will have certain percentage which are industrial area, right. So, that is what is referred here. So, in the first data point 18% is the proportion of residential land and 2.31% is the proportion of industrial land. So, in the next one there are no residential land at all and 7.07% of industrial land and so on. Okay. So, you can go through each of these variables. Okay. So, what it means is in an area where the crime rate was 0.00632 and the proportion of residential land is 18% and proportion of business acres is 2.3% and so on. The median value of the owner occupied homes turns out to be $24,000. Okay. So, this is in $1,000. So, 24 means $24,000. Okay. In a similar way, in an area where the per capita crime rate was 0.02731, proportion of residential is 0% and the industrial land is 7.07% and so on. The median value of the owner occupied homes was 21.6%. Sorry, 21.6 into $1,000 is $21,600. Okay, and so on. You have 506 data points this way. Okay. So, that is the data that we have taken. Okay. And what are we going to do by ridge regression? Very simple. We are going to, I mean, suppose you are given a new data point of this sort. Okay. So, we assume that the median value is related linearly to all the other variables that you have here. Okay. And I mean, so given a new data point, right. So, the a new test vector, okay, that is I mean assume that we are picking another region where you have some other crime rate, some other residential land, I mean proportion of residential land and some other proportion of industrial land and so on. Okay. So, if we give that, can we actually predict the median value? Okay. How close we are to the prediction? Okay. So, that is exactly what we are I mean what we are trying to achieve by ridge regression. Okay. And you can see that it is a machine learning problem, because I mean you are giving so many data points, and from this data point the machine learns that okay, if this is the crime rate, this is the proportion of residential land, this is the proportion of industrial land and so on. Okay. The house price at that region is going to be so much, right. So, that's a kind of learning that the machine does, right. So, that is why we call this machine learning problem or supervised learning problem to be more precise. Okay. So, this is the data that we are actually going to use. Okay. And if you are asking where would we get the new points, right. So, yeah, we have some 506 data points that are given to us in what you are seeing in the screen, right. So, those are data points that you have. So, where will you get the new test data, right. So, what we are going to do is we are going to split this into roughly 80% and 20%. Okay. So, 80% will be the training data, okay. So, with which we will train the machine, okay, and the remaining will be the testing data, the 20% will be the testing data. Okay. So, you have 506 data points in all in this I mean what you are seeing in the screen. So, this is one data point, this is the second data point and so on. You have a total of, as you can see here, I am just scrolling, and yeah, so you have a total of 506 data points. Okay. So, this is the last data point, right. So, 80% of 500 is 400. So, we will take 400 data points and 106 test data points. Okay. So, if you have learnt machine learning, you would actually do it like, I mean, so you would pick these 400 randomly, right. So, I mean, yeah, that requires a little bit of work as well, right. So, I am avoiding that. I am so just for the sake of simplicity, what I am doing is I am picking the first 400 points as the training data set and the remaining 106 as the testing data set. Okay. So, this is what we are going to do. Okay. So, taking this data set, we are just going to solve the ridge regression problem and check how good our prediction is going to be, our predictions are going to be. Okay. All right. So, let us write down the code for that. Okay. Okay. So, we will go down to the new and this code is okay. So, okay, maybe we will name it a little later. So, but we will start by first importing the data. Okay. So, I am going to do something which you may not be familiar with, I mean, because this was not something that I taught in week 2 when we were introducing Python. Okay. Files operation is not something that I taught, because that is more of a special application which was almost not needed for all of this course, right. I will just write the code and explain you how I mean what each step does. Okay. But if you want to learn this further, yeah, I mean you have online tutorials to learn this. Okay. Fine. So, what we are now going to do is just to import this data, that is the first step. Okay. For that I need a library called pandas. Okay. So, yeah, I am taking, so like NumPy is one of the libraries, pandas is another library which is like very useful for files operation, like reading from a file, writing to a file and so on. So, here we are actually going to read from a file, right. So, the URL is, the data URL is what I just what we just had, right. So, I can copy it down from here. Okay. Yes. So, this is lib.stat.cmu, CMU is Carnegie Mellon University, right. Alright. So, this is the URL. Now, we are going to read the data from this URL. So, you need to use this. So, we are going to read it df. Okay. And this read CSV is a command available in pandas. Okay. So, read it from data URL. Okay. So, but there are certain catches, right. So, we want to tell the computer that I mean each of these data points are separated by either a space or an enter here, right. So, I mean there are some places there are space and there are some places there is an enter, and the space is multiple sometimes, right. So, it is not like a single space, right. So, how do we tell the computer that, yeah, when you see spaces, I mean assume that the first data is over and the next data is coming, right. So, you use this command. Okay. So, this is SEP means separation. Okay. The separation between yeah, two data points is a space. Okay. So, we say S plus because it could be multiple spaces or it could be an enter or something of that sort, right. So, that is why it is yeah, S plus. Okay. Fine. And there is also another issue, we do not want all of these, right. So, these do not belong to the data, right. The data only starts from here. I mean if you just ask it to pick, I mean it will say that, I mean even the, Boston and all of these are data points. Okay. So, you need to skip certain number of rows. Okay. So, let us count the number of rows 1, 2, 3, 4, 5, 6, 7 and 14, 21 and 22. Okay. So, we will skip 22 rows. So, there is a command for that too, let us skip rows 22. Okay. And so, yeah, so it usually takes the first line as a header. Okay. So, suppose instead of writing this way they had written crim, zn and so on, it will take the first line as a header. Okay. But here we are saying that there is no header. So, do not take any header, just start with the data from here. Okay. So, that is what we are saying. Okay. All right. So, yeah, let us possibly just print the first 10 lines of the data. Okay. So, let us see if it has picked the data correctly. Okay. All right. Okay. So, yeah, I just to go through this line once more, I am this command read comma CSV, how does it read? It goes to this particular URL, it considers the space as space or multiple spaces as different data points, then you are skipping certain number of rows in the initially and you are mentioning that there should be no header. Okay. So, that is all it is, and let us see if the data is correct. Okay. So, the first data point has 0.00632, 00632, 18, 2.3, 18, 2.3 and so on, but you should have had 14 data points, but you are having only 11 from 0 to 10. in the next line there is 3 and then there is not a number for the remaining places, right. So, this is actually a problem. What it has done is it has taken one data point as two different data points. The reason is each data point is bent into two different lines, okay. Fine, I mean we need to correct this. So, I mean these are, these actually form something called as data processing, okay. At least when you are working in machine learning, the initial part of machine learning is a lot, you need to do a lot of data processing before you actually go to the actual code, okay. So, yeah, we are just spending a little bit of time doing the data processing, okay, fine. So, now you are having this data bent into two different rows, right. So, we will actually read all of these data points, right. So, from 0 to 10 on the first line and 0 1 on the second line all into x and the dependent variable into y, okay, because that is what we that is how we want the data to be, right. You want x1 y1, x2 y2, x3 y3 dot 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 x 506 and y 506, because that is we have 506 data points here, right, okay. So, let us do that, okay. Yeah, so this is no more needed. So, for x, how I am going to write? So, I should have df dot values of in the 0th row, 2nd row, 4th row and so on. I pick all the values, okay, and then I need to put in the odd rows, right. So, start from 1, you only need 0 and 1. So, yeah, if I put this, it puts 0 and 1, right. So, yeah, but you cannot just write two of them together like this, okay. So, you will have to say np dot append, okay, and it appends as the columns, right. So, this is x, okay, and for y you just need in the odd rows the second column, okay, you do not need anything else, okay. So, if you are not clear with this particular piece of code, so check this df dot values of this, right. So, this means first to last and in steps of 2, right. So, you pick all of this data in row 0, all of this data in row 2, all of this data in row 4 and so on, okay. So, you will have 506 cross 11 matrix just from this df dot values of this, okay, but you want 506 cross 13. So, you want to add these two as well, okay. So, you are appending the column at the end. So, how are you doing that? You start from column 1 and you just append these two, that is 0, 0 and 1, right, and then you go to 3, you pick these two, append there and so on, okay. So, thus you get a 506 cross 13 matrix in x. For y, you just pick the odd rows and the second column in each of them, that is the dependent variable, right. Okay. So, let us just check if we have got them right, okay. So, I will just print 10 of them, okay, and also 10 of this, okay. Okay. So, maybe we will just check a few values. So, the first row has 6.32 into 10 power minus 3, which is 0.00632. Next one is 18, 2.31 and 0. So, you have 18, 2.31 and 0, okay. So, yeah, possibly the first row is correct, and the second row is, so yeah, you have 13 values in each of the rows, right. So, this is 13 values, okay, and similarly you have 0.02731 and 0, right, 0.02731, 0, 7.07 and 0, 7.07 and 0 and so on, okay. So, possibly these are correct. And here if you check, you have 24, 21.6, 34.7, 24, 21.6, 34.7 and so on. So, yes, you have, we have got this correct, alright. So, what we have done until now, so this is no more read it. We have just read the data from statlib website, right, and we have stored independent variables in x, which is a 506 cross 13 matrix, and the dependent variable in y, which is just 506 real numbers, okay. So, now we have to split this into training data and testing data. Okay, we will do that. The training data is the first 400 of x and y, and the testing data is the next 106 of x and y, right. So, we will do, we will split that now. So, x train, x test is just this, that is up to 400 your 400th row you are picking, and this is from 400th row you are picking. Okay. And similarly, y train and y test are, you are picking up to 400 here, and yeah, so this is you are picking from 400. Okay, good. So, the training data and testing data are split now. Okay. Now, the quick thing that we can do is to verify what is the answer of the OLS problem, right, the ordinary least squares problem. Okay. Recall from the last class that the solution of the ordinary least squares problem is just given by H transpose H inverse H y, but what is H and what is y? Okay. So, H is, so you have a column of ones in the front, and this is just the X matrix, right. So, x 1, if you see the first row, you have x 1 1, x 1 2 dot dot x 1 p, which is just the p dimensional data point x 1, right, and the second one has x 2 1, x 2 2, x dot 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 x 2 p, which is just the p dimensional data x 2, right. So, H is just ones n ones added in the first column, right. So, we have the x train matrix which is x 1 1 to x n p, right, yeah, and yes, you have the ones in front. Okay. And similarly, y is just y 1 to y n, which is just y train. Okay. So, y train we already have. So, to figure out what H is, you just have to add this columns of 1 to x train. Okay. So, fine. So, H is just you insert to x train, right, a column of ones. So, that is at 0, that is before the 0th location, you add a column of ones. Okay. And it is the column, right. So, it is 1. Okay. All right. And now we have H. So, H is H and y is actually y train. So, let us just find what is H transpose H inverse H y. Okay. So, that is the beta that you want, right. The solution beta hat is, that is, it is just the inverse of, sorry, inverse of H transpose H at H at y train. Okay. All right. And so, we can print beta. Okay. And okay. So, we will first print beta. Let us see how the values of beta looks like. Oh, okay. So, there is some error. Okay, it is H transpose y. Okay, I think that is the possible error. Let us check if that is the issue. Yeah. Okay. So, yeah, this is the answer that you have. Okay. To read it properly, it is, so this is 28.6. So, beta naught is 28.6, and this is minus 0.19, this is 0.0442, this is 0.0552, and so on. Okay. So, what this means is the following. So, recall that what you are looking for is beta, and beta is given as this, right. So, if you have a new data point x, okay, I mean x naught. Okay. So, how will you find f hat of x naught or y naught hat, if you want to call it that way. So, you will find it by beta naught hat plus beta 1 hat x naught 1 plus beta 2 hat x naught 2 dot 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 plus dot 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 plus beta p hat x naught p. Okay. So, note that we have actually got beta naught hat. So, this is beta naught hat, this is beta 1 hat, this is beta 2 hat dot dot dot, this is beta 13 hat. Okay. So, with this I mean we are actually finding we have found all the values of beta. So, I mean let us actually test this. Okay. So, yeah, since beta is a vector, okay, you want, for example, so we have 106 test data points, right, x 400 to 505, right. So, y test is the actual value, okay, and x test into beta, okay, actually it is beta of 0 first minus x test into beta of 1 to the end, okay. So, this needs to be minimized, right, I mean this has to be as low as possible. So, yeah, I mean if you just print this, okay, yeah, I mean we will stop this print, I mean stop this print rather, and check how different these 106 values are. I mean this is just to give you an idea of how big or small it is going to be, okay. Yeah, I mean so these are some different values, these are 106. So, for the 400th value, I mean 400th data point, the difference is minus 7.018, 401 it is minus 12.58, the next one is minus 8.8. So, yeah, there are different ones. So, there are ones which are very close minus 0.02, there are ones which are not so close like minus 12.58, minus 11 point and so on, okay. So, note that I mean the linearity assumption is not a very great assumption, but yeah, I mean the process is very simple and what you get is this, okay. And yeah, the better metric to look at is the norm squared of this, right. So, what we do is, yeah, square this and then find the sum, okay. Okay. So, that is going to be, okay, that is 4016, okay. So, this is the error that you get, the total error that you get when you use the OLS method, okay, fine. So, I mean I wanted to start with OLS, we will move to what we do in ridge regression in the next lecture. Thank you.